All right, let's set the scene. Picture a bustling doctoral research lab. It's late at night, the glow of monitors is illuminating the room, and our main character, a super dedicated PhD student, is staring intensely at their latest SmartPLS-4 data. Today, in this explainer, we're going to follow their journey through a comic-style narrative to master the evaluation of a PLS-SEM model step by step.
So our eager PhD student literally jumps out of their chair. They point triumphantly at their screen and they declare, "My model has significant paths, so my analysis is complete." And honestly, we've all been there, right? It's the ultimate moment of relief for any early career researcher. But unfortunately, they've just made a classic rookie mistake. Suddenly, a shadow falls over the desk. Enter the strict journal reviewer character, arms crossed, peering right over their glasses. They instantly halt the student's premature celebration with a firm reality check. Not yet. You must first validate the measurement model before interpreting the structural model. You can practically see the student's smile vanish. The paths might look great, sure, but the foundation hasn't even been checked yet. Okay, let's take a breath and dive into this. To save the day, the calm, experienced research mentor character steps in. They draw a really simple diagram on the whiteboard, explaining the fundamental rule of PLS-SEM evaluation. It is always a two-stage process. Step 1, measurement model assessment, and Step 2, structural model assessment. You absolutely cannot and should not jump to Step 2 without clearing Step 1 first.
So the mentor lays out a strict checklist for Step 1. Think of it like this. Before we can build the house, we have to inspect the foundation of our reflective constructs. The student needs to check indicator loadings, composite reliability, Cronbach alpha, the average variance extracted, or AVE for short, and finally, the HTMT ratio for discriminant validity. It sounds like a lot of jargon, but it's really just a structural inspection of your variables. Let's break down exactly what these terms actually mean in plain English. Reliability metrics like composite reliability and Cronbach alpha, they simply show internal consistency, meaning the items measuring a construct are all pulling in the same direction. The AVE shows convergent validity, proving that the construct explains more than half of the variance of its indicators. And HTMT? Well, that shows discriminant validity, ensuring your constructs are actually distinct from one another, and not just accidentally measuring the exact same thing.
All right, so the student dives right back into their SmartPLS-4 output, scanning the construct reliability and validity matrix with laser focus. They breathe a massive sigh of relief as they confirm that all their AVE values are well above the critical 0.50 threshold, and their composite reliabilities are safely sitting above 0.70. The foundation is officially solidifying.
You know, there's a real visual satisfaction to this kind of data analysis. Pulling up those bar charts for composite reliability in SmartPLS-4 and seeing vibrant green across the board is incredibly rewarding. It's basically the software's way of giving you a green light, confirming your constructs are perfectly consistent and right where they need to be.
Which brings us to this essential piece of wisdom from the mentor. If constructs are not measured properly, structural paths lose meaning. This completely reinforces why that false victory at the very beginning of our story was so dangerous. I mean, if your survey questions don't reliably measure what you think they measure, it really doesn't matter how strong the relationships between them appear to be. All right, having successfully defended the measurement model, it is time for Step 2. The mentor outlines the robust checklist the student must now clear for the structural model assessment. This involves checking collinearity using VIF, standardizing path coefficients, running bootstrapping for p-values and confidence intervals, and evaluating R-squared, F-squared, and Q-squared for predictive relevance. It's a hefty list, but it's absolutely crucial. To make this easier, let's run through the ultimate study guide for Step 2. Every single structural metric has a specific job. Path coefficients show you the relationship strength and direction. Bootstrapping shows statistical significance. R-squared reveals the explained variance in your endogenous constructs. The F-squared effect size shows the specific contribution of each predictor. And finally, Q-squared and PLS predict tell you if your model actually has predictive relevance.
Now let's actually see how this works in a practical application. The student in our comic is researching a highly relevant topic: digital transformation and workforce competence in construction projects. By framing all these statistical tests around a real-world scenario, abstract math suddenly becomes a really tangible tool for solving actual industry problems.
For this specific model, our student is looking at 5 key constructs: technology integration, training support, worker well-being, team communication, and workforce competence. Remember,
The student had to check the indicator loadings, AVE, and HTMT for these exact variables first, proving they're uniquely and reliably measured way before ever looking at how technology integration impacts workforce competence.
But before letting the students run wild with those exciting structural findings, the mentor reminds them of the golden rule one last time. You should not report significant paths before showing the constructs are reliable and valid. It's entirely a matter of methodological rigor. You build trust with your reviewers by showing your work in the exact correct sequence.
Okay, fast forward to the ultimate test. The comic lab fades away, and the student is now standing in a formal examination room. It's their PhD Viva defense. The stern examiner leans forward, peers directly at the student, and poses the ultimate question. How did you prove that your findings are robust? The tension in the room is literally palpable.
But you know what? Our student is completely ready. They deliver a triumphant, confident reply. I assessed the measurement model first using reliability, AVE, and HTMT. Then, and only then, I assessed the structural model using VIF, standardized path coefficients, bootstrapping, R-squared, F-squared, and predictive relevance. They've completely internalized the mentor's two-step methodology, and the examiner nods in quiet approval.
As we wrap up this explainer, let's quickly run through the journal reviewer's strict checklist of common mistakes you need to avoid. Never interpret paths before measurement. Don't just report p-values. You need the path coefficients to understand the effect size. Don't report R-squared without explaining its actual meaning. Check VIF so predictors aren't too highly correlated. Remember that reliability isn't full validity. Never ignore the HMT. And please, don't claim predictive strength just from significant paths.
Which leaves us with this final, powerful thought to take back to your own research. A strong PLS-SEM analysis does not start with significant paths. It starts with valid measurement and ends with robust structural evidence. So, the very next time you open up SmartPLS 4, ask yourself, are your exciting, significant findings built on a rock-solid foundation or just a statistical house of cards?